Hello and welcome to this webinar on climate responsive design, looking at large and complex spaces. My name is Dr. Nugman Khan from Simscale. I'd like to welcome everyone to this webinar. Most especially, I'd like to give a warm welcome to our guest presenters today. We're joined by Madhav Munshi from Kohler Ronan, and I'm also joined by my colleague from Simscale, Ajit. Now, we're very excited to have everyone here and thank you for joining. I'm going to make a quick introduction before I hand over to our guest speakers. First of all, Simscale. Welcome to Simscale. We are an engineering simulation software provider founded in 2012, and we have 400,000 users worldwide. Why is that important, especially looking at the AEC industry, architecture, engineering, and construction? Well, we're here to empower engineers to innovate faster. The way we do that is make high fidelity engineering simulation technically and economically accessible at any scale, and is accessed by a simple login on any web browser. Now, we have access to broad range of physics for many types of users. We have architects, engineers, building service engineers using Simscale, and it's completely cloud native, which means you access it on your preferred web browser. It also works on tablets and iPads, and it comes with real-time collaboration and support. And there's lots of different scales you can model it. If you think about the industry we're in, you could use Simscale to model a small fan to look at the fan performance curve, how that might apply inside a duct or air handling unit. You can model an entire room to look at indoor thermal comfort, mixing air quality temperature, or you can look at something like pedestrian wind comfort at the city and district scale. So really it is possible at any scale to model in Simscale. Now, my colleague Ajit will talk more about how Simscale is a cost-effective solution for architects and engineers. And I'd like to quickly give you an overview of what's happening in the AEC industry at Simscale. Today, we're going to be talking about large and complex spaces, for example, theaters, atriums, semi-open spaces like courtyards. There's also a whole range of information available on our website about modeling cities. So external wind comfort, building aerodynamics, things like outdoor thermal comfort. We have a lot of users who use Simscale for data center design, for example, master planning, and a whole host of other things. You can see we are quite integrated with multiple other types of common tools in the AEC industry. The Simscale API has been used extensively by third-party software providers. Here's just a few examples. So this is, there's a urban wind app made in Rhino. This was a collaboration with Simscale and Thornton Tomasetti. We're available as a connector on NVIDIA Omniverse to visualize and import Simscale results. And there's many interactions you can see here with Grasshopper as well and Rhino. Okay, several custom scripts have been designed and other tools as well. For example, Cove tool you might recognize. So there's a lot of interactions and integrations with Simscale to common design tools you might be using. And please do ask questions using the questions panel. And this is a topic we can bring up in the end in the Q&A session. I'd like to now hand over to my colleague Ajit, who will talk a bit more about simulating the indoor environment, and then we'll hand over to Madhav from Kohler Ronan.
Thanks a lot, Nagman, for the brief introduction. I'll give it a few seconds for my screen to load, but before that, a warm greetings from my side for those who are participating in today's webinar. So this is Ajit representing Simscale's application engineering team. And today I'll be demonstrating a couple of new features from Simscale for building designers, and also give a short workflow on how you can use Simscale to perform simulations on indoor spaces. Yeah. In the next few minutes, we'll touch upon the need for CFD in designing climate responsive indoor spaces, and we'll check the couple of features which Simscale integrated newly for designers. Right. Then we jump into the platform. We'll quickly see how these features can help bring more insightful results or insightful information about building designs. And then the demo will be then followed by an interesting case study from our guest speaker, Mr. Madhav Munshi from Kohler Ronan. Yeah, and when we talk about indoor environments, right, there are quite a a lot of parameters that can influence the internal temperature, how the air actually behaves, all the flow characteristics. And these insights are really helpful in actually designing the given space for a particular criteria. For example, if you have a data center with several number of racks, then you need to make sure these racks are actually cooled down in a proper way so that they perform at a higher efficiency. And if you take the other side, if you have a restaurant, then you need to make sure you're designing the restaurant to be suitable for the particular number of occupants that's going to be there. It can be the worst case scenario where you can have like a lot of occupants at a time. And the other time, you might need to actually optimize the HVAC system so that you're not oversizing when there are no occupants or when there are less occupants. So these kind of really interesting insights are important to design a perfectly comfortable indoor space. So some of the other parameters are also given on the right side of your screen. Here you can see the occupancy metabolic rate. So this is something which we tend to actually focus a little bit when we have like a highly active indoor space like a gym or a restaurant where people can be actually simply sitting or also actually performing exercises. So depending upon that, there'll be a lot of changes in the local climate or the local environment within the space. So what CFD brings into these kind of designing is you can imagine different scenarios and then simulate them to see which one brings the optimal efficiency of your HVAC system, which one brings the optimal thermal comfort for your occupants, and such air quality measurements or air quality insights can be also predicted using CFD. Right. So this is in line with the sustainable future that we are aiming for. Instead of actually performing physical testing using the HVAC components, then you can simply use CFD and find out what's happening pretty easily. Right. In terms of these indoors environmental designs, Simscale has been working to provide like a lot of insightful features so that the design engineers can come in and get multiple insights. So one such new feature is the humidity modeling, right? So until now, Simscale was providing direct thermal comfort outputs like predicted mean vote or percentage of people dissatisfied, but with a constant humidity value. So I'll quickly jump into the platform in a couple of seconds to show you how it changed. But with the release of this new feature on humidity modeling, right now you should be able to use humidity as a participating media in your simulation. So you can actually have local humidity variations involved in your simulations, right? So the next interesting feature is all you know, those who are familiar with Simscale know that we can model solar loading by giving a date and place and the direction of the sun. Then you can actually see how the solar load is affecting the thermal comfort within a given space. Right now, you should be able to actually model these solar modules with solid regions in your CAD geometry. So first of all, this will enable a more accurate representation of the behavior. So you don't need to approximate what's going to happen on an external wall, what's going to happen on the floor or the ceiling of a building that you want to simulate. So this is a critical step moving towards modeling the entire building design using CFD. So I'm pretty excited to show these two features on Simscale. And I'll also give a quick workflow on how you can set up these simulations for those who are really new to Simscale, right? And please don't forget to actually add your questions on the questions section. So at the end of the webinar, we'll try to cover most of the questions that is coming from the audience. Yep. Let me quickly jump onto the platform. And those who are extremely new to Simscale, Simscale is a cloud native simulation tool. So all you need to do is go into simscale.com on a browser. You don't need any particular hardware, so you can log in and then you can start simulating directly on the cloud itself. So this is what I have done for this indoor comfort analysis of a restaurant space. So on the screen, you can see the results of a CFD simulation where we have actually given certain inputs, certain ambient conditions, and also the HVAC inlets. And we're trying to find out whether the HVAC supply is enough to actually satisfy the thermal comfort of the occupants inside, right? And previously, you should be able to see the normal outputs like temperature, density, the pressure or the velocity characteristics within this room. But now what you have in addition is the percentage of relative humidity. So this parameter will give you the local distribution of what is the humidity at this particular location. So if you find out the humidity, then at the particular point, then you can actually use this to see whether your HVAC is performing properly, whether you need to actually supply a higher humidity in case if you're in a dry or a desert area, or lower humidity if you have like a already moist environment around your restaurant. So such insights can be easily found using these new features, right? So one interesting thing will be checking out the humidity at the human level. So for example, there are a few occupants inside this restaurant. There is a bunch of windows open on one of the sides. So you can see the humidity creeping in from the outside environment, and slowly it disperses, and the distribution actually changes depending upon the HVAC inputs from the top, right? So you can see just near the window, which is open, you could see higher percentage of relative humidity. And then when you move away from the window, it actually reduces. And this will affect the thermal comfort of the occupants sitting inside. So I can quickly switch back to the predicted mean vote, which will give you the thermal comfort indices for these occupants. So right now we can see the occupant sitting near the window has about 1 predicted mean vote, which means they are a little bit uncomfortable. So on the verge of actually feeling the heat. And when you move towards the other side, it's about like a higher value because of the humidity difference and the temperature difference prevailing in this particular space. So that's about the humidity. So in detail, you'll see a lot more results and how this can be used in an actual scenario. For example, the theater hall, which is going to be presented by Madhav from Kohler Ronan. But the next feature that we'll be looking at is the introduction of solid bodies with the solar module, right? So I'm going to switch back to a different simulation setup. So you can see right now, you're not just limited to only air or the fluid medium for your simulation. You can also add particular solid or specific solid materials in your simulation to find out the thermal comfort or the temperature difference in your simulation. So let me quickly open one of the results and show you how it looks like within Simscale and what kind of results you can get. But while the results are loading, so those who are new to Simscale, if you want to actually do this simulation, you can pretty much sign up. And if you have questions on setting up a simulation, if you have a doubt on actually how to check the mesh or how to actually check the results, you can simply use our in-platform support chat, where you can send us a message stating, hey, I'm new to Simscale. Can you please help me set up this simulation? Then we're happy to actually switch back to a demo or respond here according to your questions, right? Coming back to the results here, you can see right now we have solids involved in the simulation. And when you go ahead and display the temperature, I really like Celsius for the units. Makes much more sense than Kelvin. So right now you can see there is a huge temperature difference between the ceiling and the bottom of the ceiling as well. So if you look inside, probably we'll hide a few faces here to see how it looks inside, maybe decrease the gradient. So right now you can see this is all red in color because there is a solar load applied on these direction. And then you can see the temperature gradient from the ceiling top to the bottom of the ceiling. And here we have included also the steel frames in the restaurant. So now you can see how the temperature is actually creeping in through the steel frames and not through the false ceiling materials. So this will give you a lot more details about like the kind of insulation that you can use for your building or your design space, or the kind of materials that you want to use for your window frames. So you can actually check for thermal bridging uh, results or phenomenons happening at your window frames. So those kind of results are now enabled using these two features. So I'm pretty sure this will be interesting for all the building designers. So take a spin at it, log into Simscale and try to actually simulate your own cases, and we'll be happy to actually support you on that. And right now, again, just to remind, if you have any questions, please feel free to put in the questions section. But now I'll hand it over to Madhav to actually see how Kohler Ronan uses Simscale to actually simulate some of their indoor spaces. Madhav, the stage
Thanks,
is
Ajit.
yours. Yeah.
Thank you. Awesome. Thank you so much for joining us. Pretty excited to share our work and collaboration with Simscale. So just a little bit quickly about me. My name is Madhav Munshi. I work with Kohler Ronan Engineers. I have a background in architecture and a master's in climate responsive design as well. I'm an ASHRAE building energy modeling professional and have a LEED AP certification as well. Overall, have 15 years of sustainable design consulting and energy analysis background. Most of the work that I've been part of has been buildings for public use, such as schools, libraries, museums, and performing arts centers. I'm pretty excited about the decarbonization and net zero movement, adaptive reuse of buildings, and in particular leveraging technology and cloud computing tools to solve complex building design issues. And Simscale has been a great partner. We've learned a lot. So really happy to be here. A little bit about the firm that I work for, Kohler Ronan Engineers. Founded in 1998, we are a full, for people in the US versus Europe, we are a full mechanical engineering company, MEP, mechanical, electrical, plumbing engineers, fire protection, AVIT, commissioning, and energy analysis services. Led by about 7 partners. We're based in 2 locations, New York City and Danbury, Connecticut. We're about 70 professionals with 22 professional engineers and about 18 lead professionals. Our specialties and a lot of the work that we do involves museums, performing arts centers, libraries, university, independent schools, and historic and landmark projects. Some of the work that I've worked on, and actually the Metropolitan Museum of Art, I'm going to cycle through some project images that are projects that are obviously our most exciting, most challenging, as well as where we've leveraged CFD to provide solutions and feedback for our design. So at the Met, which is some of you might be familiar with it, it's almost 2 million square foot of artwork, lots of different wings, super complicated building environment, temperature and humidity maintained at constant temperatures, constant temperature, constant sort of conditions, super complex workflow, especially because you're working in spaces where the artwork cannot be disturbed. So you're trying to really work around a lot of the spaces inside. We're adding a lot more, sort of doing a lot more work inside the spaces, and CFD has been really helpful trying to understand how we approach our building design over here. Other project, the Princeton University Art Museum with AJ Architects and Cooper Robertson. Again, this is a brand new addition and a restoration of an existing building. Very, again, complicated artwork, complex building structures. We're using a lot of new technology of construction as well, timber-based and concrete, mix of all of that. So, when you're working with such environments, CFD has been really helpful for us to figure out how we're distributing airflow, where we're returning from, where we're supplying from, and are we maintaining temperature and humidity continuously. Another one, a little bit south, like the first 2 projects are northeast of the US, where the climate is cold and humid. But as we go down south, we were working also in Memphis, Brooks on the Bluff Art Museum with Herzog & Miron and Archimania. Some more hot and humid conditions over here. So again, we have to be really mindful of how we're treating artwork inside these spaces. And finally, the project that we're going to talk about a little bit more in detail today, the Lincoln Center, David Geffen Hall, with Dimensional Architects and Todd Williams, redesign. This was a really huge effort. We finished it. We started in design, finished design just before COVID, and all through COVID, they accelerated construction, and the building is open and has been super successful. And the response from just the audiences and media as well has been really amazing. So we are super happy that this turned out to be successful. And many thanks to Simscale as well for being our partner for making that happen. So integrating CFD, I want to spend a little bit of time sort of talking about what happened. And, when we started doing CFD, a lot of the spaces that I've shown you and the buildings that we've shown are very atypical, super complicated spaces and buildings. There are location-specific changes, there's design-specific sort of requirements. A lot of them are also driven by artwork or the function that they are in, right? So in addition to load modeling and standard sort of load calculation tools, we realized that we needed something that would help us to visualize airflow and sort of give us that proof of concept level of analysis that would give us feedback as engineers, mechanical engineers especially, about where the airflow is going to be. Are we mixing properly? Are we supplying at the right temperatures? Is it stratified condition? Is it a fully mixed condition? All sorts of stuff that we need to be careful of. Are we providing ventilation? Is everybody getting adequate ventilation, right? So there's a lot of questions that we need answered. So we started looking at CFD pretty early on. I think probably about 8-9 years ago. We've started working with other sort of software tools and getting CFD more and more into our practice. So these are actually, so the images I'm going to show you actually are newer images. And David Geffen Hall was actually our first project with Simscale. But for in this particular project for the Brooks on the Bluff Museum, we were trying to understand how the gallery spaces were affected with occupants, temperature setbacks, with thermal comfort, and if there's stratification and stuff like that happening. A lot of the galleries are really tall, and so we wanted to make sure that however we are supplying in the air, if it's airflow or supply temperature, we want to make sure we don't have the stratification that you see on the image on the right, where the entering air is coming at a 68 degree Fahrenheit, like cold down draft coming down, and then you have a stratified condition inside the space. You'll be looking for a much more, on the image on the left is kind of a much more ideal condition where we have a mixed air condition with a 2 degree differential throughout the space. You don't want the condition on the right. But again, we are trying to balance not just temperature and humidity, but we're also trying to make these buildings energy efficient. So the idea of using Simscale or any sort of tool that we can do iterative modeling was really, really helpful. In this example, at Princeton Art Museum, we had different types of ceiling configurations that we were using to sort of, again, condition the space. So we wanted to make sure that either, again, looking at supply temperatures, airflows, velocities, location of return air locations, understanding how airflow will move within the space, looking at velocities and also at temperatures. So looking at all those conditions, making sure that everything that we're designing is making sense. And for the main event, let's look at David Geffen Hall. Again, so David Geffen Hall, I think about 2018, 2019 is when 2019 is when we started working with Simscale. And we were using a much more, I would say, simplistic CFD software before, and we realized that we won't be able to do the level of modeling without sort of scaling up to a much more robust tool. The options out there were Fluent and other more physics-based demanding software, which needed a lot more computational power as well as skills. And we literally happened to stumble upon Simscale, and we started talking to them, and it just turned out that it was a perfect fit for our application. So before going that, a little quick background on David Geffen Hall and Lincoln Center. Lincoln Center is an institution in New York. It is the home of the New York Philharmonic, premier gold standard orchestra. They're traveling all over the world, but this is their home. This is where they perform. So they really wanted a space that was theirs. It needed to be brand new. It has to be transformative. And the original sort of the space had a lot of acoustical issues, and they wanted to sort of change all of that and create a more intimate experience for audience members as well. So you can see over here in this picture, the orchestra is sitting right in the middle and surrounded all around by audience members. So that sort of was the whole design approach. The architects on this project were Diamond Schmidt and Todd Williams Design. And acoustics was provided by Acoustics, and theater design was Fisher Dax Associates, and Kohler Ronan provided the mechanical, electrical, plumbing, fire protection services and services as well. And we also did a lot of testing using CFD. So the objectives of, we were doing design, but I think what happened was, because we were working with an existing space, there was a lot of constraints in the way the amount of airflow that we could introduce into the space that was already set, because we were using existing distribution pathways. So we wanted to make sure that with the design that we had, we were able to maintain thermal comfort within the auditorium. We wanted to observe temperature and airflow velocities for the different orchestra conditions, depending on, there was lots of acoustical configurations involving baffles that would open and close depending on the type of performance. And we also wanted to make sure that we could adjust airflow and temperature set points to meet these acceptable conditions. Again, we're testing lots of different configurations over here. But the final testing happened actually on site. A lot of testing and balancing happened, to make sure that the airflow was coming out properly. But using the CFD software, using Simscale, really allowed us to test all these different ideas and sort of come up with at least a few ways to start our on-site testing. So the CFD setup, like I mentioned, this was our first and our largest project with using CFD, and this was around 2019, 2020. And Simscale, if you've been on Simscale now versus what it was like even like 3 years ago, it has a lot more features now, which is actually one of the things that we love about Simscale, is that this continuous refinement, this continuous improvement about the way the software is. So we work with Revit models and Rhino models that we brought into Simscale. We had to do a large amount of cleanup of the Revit model. Just sort of, Revit models are plagued by surfaces that don't connect and don't join, especially in such a complex space. We were importing into Simscale literally on a daily basis, testing multiple times, like making sure it worked. We are able to create a mesh lots of times. And then it finally worked, which was great. Where it worked, it was beautiful. So the model looks a little bit like this. So if you can see in the middle, there's acoustical baffles to the left on top, those sort of curved surfaces. We sort of got the seating in properly. We have the stage. We have all the audience members, audience sort of seating areas. There's supplier. We put in supplier diffusers, returner diffusers. We also put in people loads. Actually, we put in blocks of people so we could actually capture the heat output from the people as well. So a lot of details went into sort of creating this, developing this geometry and the whole volume, if you may. And we did multiple. There was a lot of. We changed it multiple times as well, just to get the right configuration. Just from a different angle. Yeah, okay. And as we started testing the CFD, we started making small adjustments to make sure it was working properly. One of the things that we realized was that obviously the diffusers, and when you have an angled surfaces, again, just some silly stuff like it will automatically model everything was coming down normal as in perpendicular, but we wanted to sort of create different angles. So we were, lots of notes were sent back and forth between us and Simscale that, hey, we are seeing this condition where the diffuser is really throwing at this angle, but it should be throwing at that angle. So it was really fun to sort of do all of that, fun and challenging at the same time. And again, you start seeing these really like interesting conditions that happen, where you can see over here that you're at the ceiling, we have these acoustical curtains that were falling. Air would at some temperatures and airflows, air would cling to those curtains, and in some conditions that it wouldn't. On the left, in the balcony side, we saw that the air was actually getting pulled out instead of going back inward. So we were able to change the angle of the throw angles of those as well. So we started zooming in and out of like multiple different sort of spaces, and it got some really great feedback. One of the really interesting feedback was happening right at above the stage, was that we had this sort of big duct that was coming downward to supply, and we were throwing only on one side, but we ended up adding like a sort of like an alternating, one was throwing to the right and one was throwing to the left sort of configuration. So again, looking at those kind of configuration sort of, you can see over here, the acoustical baffles are actually open, and at the bottom, you can see those baffles are closed. So there's, it's a lot of things that were changing continuously. This is a very dynamic space, and we had to sort of test multiple different configurations to see and making sure that our design worked for all of them. So it was fairly challenging as we sort of went through the whole process. Like I mentioned before, we found one of the cool things that we were obviously happy to do is the whole idea of using this sort of CFD is making sure that you find all the issues, that you anticipate all the issues and you find them before everything gets built up. So we found that the airflow in the balconies was not adequate. And the directionality also was not adequate. So we ended up adding more airflow, moving airflow from the front of the hall to the back of the hall, because the total amount of airflow in the space was constant. So we just ended up moving it from the front to the back and change direction as well, so that the balconies were going to be more comfortable for the seated occupants. So this is like we had like these 4 different configurations. We had the symphonic, the rental, the film configuration. We also had a graduation configuration, which is when the whole theater was going to be full of a lot more people. So it was going to be much more sort of heavily used space. So this is just showing the section. And then the main visualization of the big sort of the big space. When we started testing, we were looking at, like I said before, we tested. We moved airflow from the front to the back, and we started looking at air temperatures, stratification, and where we started finding those balance points, balance conditions, right? So in this case, we will sort of, for one of the configurations we looked at, we found that supplying at 55 degree when it is fully saturated space, we still sort of experienced some sort of downdrafts. And sort of these central columns of like cold air. So when we sort of relaxed to like 58 degrees, it became a little bit more sort of more homogeneous, more mixed condition, and comfortable again for the occupants. Same with velocity, like that was temperature, but velocity as well became a little bit more relaxed when we sort of went from 55 degrees to 58 degrees. And it was a bit more, we felt that again, we had the ability to control it as well in reality as well. So, but we were just testing our proof of concept, like, okay, we can do sort of these sort of sequences, and it will help us to sort of change from if we are finding that it's getting colder or the occupants are uncomfortable, we can reset to 58 without doing any physical changes, just resetting temperatures a little bit to keep occupants comfortable. Again, for when the baffles are open, these cases were baffles closed. If you see, this is when the baffles are open. You see a little bit. You see that the air kind of just like dumps. Sort of, we saw that like air, there was a danger of air just dumping downwards and like creating this cold mass. So again, resetting these temperatures helped us get those ideal temperatures for that we were expecting. Again, proof of concept, which was working fine. Once we sort of did all those tweaks for moving airflow from the front to the back, we were sort of seeing those that the theaters was controlled to very good levels. At the stage, which is very, very important as well, because the Philharmonic wanted to have, you don't want, when you have like sheet music on your in front of you, you don't want like airflow and things flying away. So we wanted to make sure that we gave them the temperatures that they're expecting. So I think the target was under 20 feet per minute of airflow around the occupants. So I think we were quite happy to sort of see that also showing up in our simulations. This is both airflow and temperatures. Stage is maintained pretty well at 70 degrees Fahrenheit. Velocity gradients are also minimized. This is for a configuration where we had like a screen in the background. We would have an orchestra and a screen. There's lots of different ways that this data was going to be used. So we had to really test all these different configurations. So that was really great. I think at the end, before the theater opened, obviously everyone was at the site. The controls guys, our engineers, the owners, and everyone, and even the acoustical consultants, right? This obviously, if you think about it, there's a lot of different drivers. Acoustics is really, really critical. And whatever's happening in the mechanical systems happening in the background. So there can be no disruption to the acoustics, regardless of what is happening on stage. Acoustics, regardless of what is happening at the mechanical side. So it really made a big difference, and I think the results were really, really satisfying. So some of the lessons learned were that supply temperatures could be reset. Now, one thing I want to mention is that this whole space is actually inside. There's no external. There's no solar. There's nothing. Like there's things happening above it, on the side of it, and the back of it, on the bottom of it. So there's like this whole space is within sort of a bigger box. So none of the walls are exposed. So we were anticipating that once we start conditioning this theater, temperature and humidity should be fairly maintained. Obviously, the only thing is we're going to have now going from 0 people to like 3,000 people, like lots of people in the space. So that obviously is a lot of stage, and the stage as well. So making sure everybody stays comfortable is important. Stage to be maintained about 70 to 74 degrees. Obviously, we saw that there's a lot of these red spaces, but now we realize there's people over here, furniture, chairs, lots of finishes and fixtures that will really sort of make it a lot more smoother than you see a lot of turbulence, which is over here, but in reality, it will be even more smoother. For our design and for the acoustical design, we sort of informed that if we can increase the gap between the reflectors and the acoustical baffles, it is a little bit more desirable, so that air doesn't there's no pressure created between sort of those gaps. We've increased the airflow at the balcony supply outlets, so that was really good. And we also introduced there are these light wells which are in the center of the ceiling. We introduced a multi-directional airflow pattern that sort of created a mixing condition instead of like a straight linear diffuser that just dumped straight down. So that was something that we definitely introduced, and we added those changes that sort of really made the design work really well. And from simulation side, and working with Simscale especially, cloud computing really simplifies the extreme computational requirements of CFD. We were running I think if you were running this on our machine, I don't even know how long it would take. But with the availability of running this on the cloud, we were running these simulations like it still took time. Like this was a very computationally intensive simulation. I think it still took a lot of time to get to convergence, but it was definitely a lot faster than we could have ever imagined and we could have ever hoped. Simscale, again, because it is a continuously refined interface, we were getting functionality added as we were doing the work, which is really great. The step-by-step interface that they've set up was really helpful. It really minimized a lot of the errors. Like you just literally went step by step to set up the whole file, which meant that you won't have any errors. We did find one really funny situation where my gravity vector was inverse, where instead of the air flowing down, my gravity was actually going upwards. So I think for the initial 2 or 3 runs, we just couldn't figure out what was going on. So, but that was funny. That was like one of the funny things that happened. Like, why is the gravity reversed? And then we just figured out, oh, okay, it's just fixing the sign, the plus and minus sign on it. Again, lots of tutorials and help guides. The ability to run multiple simulations was really helpful. We could set up the model and test multiple scenarios without really waiting for each scenario to run individually. So we were running multiple things at the same time. The results visualizer is also really helpful. We were able to cut and sort of view and zoom in. And obviously, we on Kohler Ronan side are now really excited about the humidity modeling, because that is definitely a metric that is a lot harder to control, especially in museums. The ability to have that level of detail is really helpful for us as designers. So we're excited to sort of do the next steps and for next projects as well. And they have a great team of specialists that are always there to help you, lead you, hold your hand sometimes, and give you moral support when things are really breaking down. So it's a really great tool. We've used it multiple times. We use it a lot now, and really helps to sort of give us that peace of mind on that our designs are we're doing the right thing, we're proposing the right design, and again, we're leveraging it for comfort, satisfying stakeholders, energy efficiency, so all the sort of key things that are needed for project success are being handled by Simscale. So that concludes my presentation. Thank you all for the time. Nagman, back to you.
Madhav, thank you so much. I really enjoyed your presentation, Madhav. And one thing we all have to appreciate is you've shared a lot with us, right? And we on a very complex project. The space is huge, right? The volume is yeah. And I'm applying CFD at this scale. Most people in that industry use CFD in a room, right? Like a small room or a data center. You've done it on a huge volume. And it's been hard, right? It's a big project, and the results are critical. We've all been in theaters that are too cold or drafty, or you can't hear something. So we appreciate this work that you've done. Thank you for sharing with us in a lot of detail and all the time you've spent putting this together. And we have a lot of questions for you, Madhav. Should we take some questions from the audience?
Yeah, sure.
Brilliant. I love your story about the negative gravity. I'm sure you'll be designing buildings in space soon. That feature.
I know, right? We're ready for that.
Absolutely. So, Madhav, I have a few generic questions and then some very specific to the project. Okay, and then there's some questions about Simscale, which maybe I'll hand over to Ajit to answer as well. And a bit about yourself, Madhav. Interesting comments you made earlier about using other CFD tools in the past, other building simulation analysis tools. You're ASHRAE building energy modeling professional. Tell us a little bit about what that actually is and how that fits in with your use of multiple types of analysis tools.
Well, obviously, the ASHRAE building energy that certification is a really great certification for anybody who's in the building simulation energy analysis industry. You know, you need to sort of really understand physics, thermodynamics, energy consumption of all different things that are going to affect a building's energy use, the impact of HVAC systems, thermal comfort, materials, calculating thermal U values of envelope assemblies and all that kind of stuff, right? So I guess my kind of, and I have a background in architecture as well, so it took me a little while to understand systems, but then I started working with engineers, and now am I an architect or am I an engineer? I don't really know anymore. It's kind of the lines are blurred. But the building energy, having that sort of certification, there's testing and continuous education credits that we need to sort of go through as well. But that really sets us up as those type of professionals to sort of to push the boundaries a little bit more and work with something like a CFD. Now, CFD traditionally, if you would ask me a few years back, I would have said, I don't think I'm qualified enough to do it. But then we started with simple box models and working again with, now I work with engineers, professional engineers who are really, really smart. And they really know exactly what's going to happen in the space, but they don't necessarily use the tools that us as building simulation specialists, we are very comfortable with using different tools. So I feel like the BEMPs are perfectly sort of, Azure BEMPs are perfectly sort of placed to sort of pick up from where engineers leave their designs and sort of use that information and feed it into some sort of a CFD software. So definitely I would encourage a lot more people to try this out.
A fantastic point, Madhav. Really appreciate that. It fits in a lot with what Simscale is saying as well. You know, you don't have to be a super CFD expert to get started, right? With these tools just on a web browser. And you've done exactly that, and now you're simulating these huge theater spaces, right, which affect that where you have thousands of people in attendance. Okay, thanks so much. We have a couple of questions on the David Geffen Hall design, right? So I've just put two together, Madhav, because they're related. So one is about the acoustics, and I know you mentioned there was an acoustic consultant on the project as well. So what impact did the HVAC and the mechanical equipment have on acoustics, and how was that factored into? And a little bit about, did any aspect of the lighting and acoustic models fundamentally clash with the HVAC design and requirements? So two related questions for you.
Absolutely. So acoustics is primary. If you're in the performing arts theater, if you're in a performing arts theater, you're listening to the music, and it's all about, and lighting as well, visual, the quality you're able to see. Like if you, I'm gonna scroll back a little bit so we can have the visuals of the theater, right? You're seeing the performers and you're hearing the performers. The HVAC should be this sort of, it should just work, right? That's what everybody wants. The HVAC is unfortunately secondary because you're trying to really optimize. The acoustics comes first. Everybody is just talking about acoustics all the time. And we had a great acoustician, Paul Scarborough, who's brilliant. Done a lot of work in like lots of really amazing performing arts spaces. So in acoustically, the acoustical baffles you see over here as well, right where the lighting is. There's a lighting, you have lighting, and you have the acoustical baffles, and there's HVAC also right above that. So we're all working and fighting for the same spaces. So it was again challenging, I would say, to sort of make sure that we're providing the right amount of air, it's coming at the right temperature. So there's a lot of back and forth. And in this case, we were really able to work closely with the acoustician as well, asking for, hey, when you guys are in a closed condition, when you are in this closed condition over here at the bottom, could you give us a little bit more space? And they were like, sure, I think we definitely can do that. What we later found was that acoustics comes, and that the final tuning happens when the building is completed, and they come in, and then they sort of move around their baffles and move around everything and making sure they have the best sound. So it's a really it's amazing to see the kind of work that they do. We were obviously, and again, everybody's on the site together. It's really a team effort, because with every adjustment that they make, we have to make sure our airflow is balanced properly. So we have different sequences built into our program that sort of change the supply air temperature, the supply airflow as well for the different acoustical configurations. So a lot of back and forth. I'm sure my engineers, the engineers on the project, would have a much more different answer. But from what I know, that's the story.
Excellent. Madhav, just a very quick related question to that. One of the members is asking about the use of natural ventilation, right? In a big space like that, maybe during the mid-season when the temperatures outside are quite pleasant, for space this big, and you mentioned energy efficiency requirements as well. Is that something that's ever considered for spaces like this?
So what we do to so we actually took a look at natural ventilation hours in New York City. So there's a couple of ways we do it. One is we do run the whole air. If the outside air conditions are perfect, we run the unit in full economizer mode, right? Which means you're bringing in 100% outside air, you're bypassing the cooling coil, and you're just using the fans to provide air directly. But you still need to go through, because you're working with material finishes. You also want to control your humidity, which is really critical as well. So, if you're in New York City, there's a lot of noise all around us. So it gets difficult to sort of rely fully on. You can't really just open windows. That's not going to happen, because again, this is an enclosed box. But we were able to use a lot of economizer whenever we can. So that's all built into the whole system design.
Brilliant. Okay, Madhav, two more questions for you. You mentioned a little bit about importing Revit models and Rhino models and spending time on the CAD preparation, I guess, for simulation. So we have several questions actually. I'll just bundle them all in one. Could you just elaborate a bit on your, because a lot of to many people the barrier to simulation, I guess, is the CAD models, right? Importing from different BIM tools, architectural tools, and different types of model qualities. So some architecture models are super complex, and that complexity is not really needed for simulation, right?
Correct.
Maybe just elaborate a little bit on what you said earlier about you and your team and your journey to making this workflow a bit more seamless.
So, well, that's the challenge for whether it's a CFD or whether it's building energy modeling, right? This has been a challenge, and this has kind of been the discussion for years and years. Well, 15 years since I've been doing this, because we have to use the same process for energy models as well. You need to sort of take the Revit model or the architectural model and translate it into something, into either energy or, in this case, CFD. So in this case, again, we had a really good partner on the architectural side who was continuously giving us models, because again, the problem in this case, we identified it together collectively as a group, that, okay, we need to understand this as a group, this is a collective exercise. So we're a really great team that was sharing models back and forth. And then once we understood the different configurations, it was really just me and my partners and my colleagues cleaning out the models and just removing unnecessary information. I agree that this becomes the BIM model to a BEM model, or the building energy model, or a CFD translation model is challenging, and we all, some people on the panel know how much time we spend cleaning up the geometry. Sometimes we found that, like in these cases, sorry, I'm going to go backwards.
Yeah, Madhav, is the energy model and the CFD model the same, or not necessarily?
Not necessarily.
Okay.
It's software driven. So it's depending on which tool we're using to solve. So in these cases, right, we had the BIM models, but we created our own rooms and boxes. So we realized that we don't need to sort of use the BIM model. We created our own boxes to solve these two cases. But for this project, which was geometry driven, we had to use the BIM model. There was too much detail that we didn't want to miss out on, so we kind of stuck to sort of using the BIM model to run our CFD analysis.
Absolutely, makes sense. Madhav, there's a couple of questions about Simscale. I'm just going to switch to Ajit quickly to answer those, and then I'll come back to you for some final closing remarks. Okay?
Okay.
And Ajit, so a couple of questions related to what Madhav has been saying. I guess the first one is about Simscale and importing CAD. Maybe, you know, from an architect, from an engineering perspective, the type of AC models we typically encounter. What's a good starting point or strategy, and what kind of CAD models can be imported into Simscale? And the second question, we have an attendee asking, what's a good way to get started with Simscale? Links and advice on tutorials, etc.
Yeah, definitely. Those are two great questions. So, talking about the CAD models, as Mother mentioned, I mean, if you want to actually add a lot more details into a simulation, so the best place to start is actually having a BIM model and then starting to strip down what is not necessary or relevant for CFD, right? So, for specific tools like Revit or any other architectural tool, there are options where you can find or you can set templates for simulations and templates for like BIM or HVAC or lighting modeling, right? So you can actually strip down all the details like doorknobs or sometimes the grills that are not significant for the flow. Then you can actually strip down and keep that as a template for simulations. So that's how many of our customers actually do. They have like the original model with all the details for the BIM analysis, but then a stripped down version for simulation for quick geometrical or configuration checking. So that's how the geometry workflow looks like. And when it comes to Simscale, we do support quite a lot of native file formats, including Revit, Rhino, SolidWorks, Autodesk, or any other tool that you can name from the market. So the translation between these tools, that'll be smooth enough, so you can actually import a native file format. But the major work is on the CAD tool, where you need to actually decide whether to keep a detail or not, depending upon the speed of simulations that you require, and also the detail of the results that you're needing to see in a simulation. I hope that answers the questions. We do have quite a lot of documentation regarding like how you can use Revit model for CFD or any other model for CFD. So we can also share it back if you have specific questions on that. Yeah.
Thanks, Ajit. And we can maybe in the follow-up email that goes to all attendees, we can include some links to tutorials, and we have some YouTube tutorials and getting started guides as well. Thanks so much, Ajit. Madhav, let's closing remarks to you. What's next for you and your team in terms of using CFD, either on some interesting projects, maybe some new features you want to try, something experimental? What's coming up for you guys?
Oh, I'm definitely excited about the outdoor thermal comfort model. I know we've spoken extensively about it, and master plans are exciting, a little bit different. In addition to, I think, testing those features out are definitely next on my list for Simscale, and humidity modeling as well. Actually, temperature, even in our energy simulations, temperature is easier to control, but humidity is a whole another level of complexity. So those two features are on my list of, or on our list of testing for our next generation of museum and performing arts projects.
Brilliant, thank you, Madhav. So you're more interested in looking at some of the new features like Ajit just showed today, humidity, and also some of the external comfort and external aerodynamics, right? So pedestrian wind comfort. Oh, that would be super interesting. We'd love to have you back maybe a year from now, Madhav, and share a presentation where you showed us, some cool projects you worked on with some of these new features.
Looking forward to it, yeah.
Brilliant. Thanks so much. We're top of the hour. Again, I'd like to say a big thank you to our guest speaker from Kohler Ronan, Madhav Munshi. Thank you for joining, Madhav. We really enjoyed this. And to my colleague, Ajit from Simscale. Everyone who's registered and attended will send a follow-up email with a recording of this webinar and some additional resources in the email. Thanks so much for joining us today. Thank you and goodbye.
Thank you.
Thank you all.